This is Lab 2, Lines of Charge. So this lab is very similar to Lab 1, since our main goal is to find an estimate for the charge on an object. In Lab 1, we looked at the tapes as point charges in order to estimate the charge. But in this lab, we will split the tape into many point charges and add up all the contributions of force between the points in the two tapes to determine an estimate of charge. Some of the major physics principles we looked at in this lab were Coulomb's law, the momentum principle, uniformly charged lines, and charge interactions. For much of the lab, I used clear Scotch tape as my object that became charged. Through the use of previous observations and calculations done with my computational program, I found the charge on the piece of U tape to be roughly 2.2 times 10 to the negative 8 coulombs as we split the tape into more and more pieces. Because the setup of this lab is identical to Lab 1, I used the same values and observations from the previous lab, where we used the setup illustrated in the diagram on the right to observe the charge interactions between two pieces of tape. I then set up my code in GlowScript using these initial values, where I created a computational model of the two tapes divided into many smaller points, which enables us to observe the electric field and force interactions between each charged point and use the sum of the electric force of each point to find the estimate of the charge on the tapes. So now we move on to the actual code and models. So we begin with inserting our constants for K and G, and then we also insert our observed values, which we use Q equal to 9.33 times 10 to the negative 9 that we get from our last lab where we estimated just using point charges. We also insert our function for calculating an electric field that we used in previous labs. And then we use this next function given to us to create our two tape models where each tape is created as a line of in points, and we have our separation distance here and then the length of the tapes here. We set the scale for our electric field vectors and our force vectors. And now we move on to the actual computations. So this function takes each point in tape 2 and iterates over each point in tape 1. And so for every point in tape 2, we calculate the electric field from that point on each point in tape 1. We add up all the points in tape 2 affect electric field on one point in tape 1 to give us this E at dq1. We can also find the force from each point in tape 2 on points in tape 1 by multiplying the charge of dq1 times the electric field calculated from one point in tape 2 on one point in tape 1. This is Coulomb's law. So this will give us, when summed up over all the points in tape 2 over all the points on tape 1, will give us the force from tape 2 on tape 1. So here we create the electric field vectors by taking the sum of each net electric field at each point in tape 1 and multiply by the scale. Down here we create the force vectors for the electric force, which is just the summation we got from our function. And then for the gravity, we know that the y component should be negative mg. So when we run this, we can see our electric field vectors on the red tape, which is tape 1, and blue is tape 2. We can see our gravitational vector. But we see that the electric force and gravitational force are not equal as we expect them to be based upon the momentum principle in our calculations. This means our estimate for point charges is not very accurate. So we go back and we would eventually have to plug and chug and figure out a different kind of solution for this, but we found that it's about 2.26116 times 10 to the negative 8 coulombs will result in an electric force roughly equal to that of the gravitational force, which we can see here that it's 1.962 times 10 to the negative 3, which is equal to 0.001962. So then we know that lines of charge, that as the number of divisions on the line increase, the more accurate the electric force will be. And so therefore, the more accurate our estimation for the charge should be. So if we look at it for 50 points, we now know that the charge should be about 2.2146 times 10 to the negative 8. And as we can see here, the gravitational force and electric force are equal. And if we furthermore go on up to 10, up to 100, and even thousands, it generally approaches 2.2 times 10 to the negative 8. And as we can see here, for 100 points, they're still roughly equal. Some of the questions posed to us were, what if you had modeled each of your tapes as a single point charge, like in the previous lab? Compare these values. So for the first lab, we got 9.33 times 10 to the negative 9 coulombs for the point charge model. However, in this lab, we estimated that the charge on the tape should be about 2.2 times 10 to the negative 8 coulombs. This is about a 57% difference in values. Now, these values differ because a piece of tape that is roughly 20 centimeters long cannot be reasonably modeled by a point charge. So modeling the tape as a line split into many pieces will create a more accurate estimation of the charge on the tape. Therefore, the charge estimation for the computational model where n equals 100 is more likely to be closer to the real value. Through using point charge models and physics principles such as Coulomb's law and uniformly charged lines, I created a computational program to calculate an estimate for the charge on a piece of clear Scotch tape as 2.2 times 10 to the negative 8 coulombs. This lab provided a great illustration of how making assumptions when doing physics calculations can cause large differences in outcomes of these calculations. Thank you.